So there's some important considerations when we're doing these power rankings, and that's that the relative power rankings are dependent upon sample size and underlying distribution. So some sample size considerations, we can use these charts from previous research to help determine our order of tests. So here you'll see that as our sample size increases, in most cases, so does the power. So the maximum power is 100% rejection of the null hypothesis, and 0 would be 0%. So this gives us a really great visual representation of the power comparisons. And something that I find really, really fascinating is you'll see that this KS test kind of peaks right here and then sort of flattens out around 16%. Another really cool thing is that in the beginning here, you'll see that the Shapiro-Wilk-Royston is more powerful than the Lilliefors, even though they're very close, and they're basically right on top of each other. But then right between that 50 and 100, the Lilliefors converges onto 100% really, really quickly, whereas the Shapiro-Wilk sort of approaches much more gradually. And then the Ryan-Joyner catches up to that near 100%, right around 500. And something really interesting is that the Anderson-Darling kind of do a swap, with the Anderson-Darling being more powerful at a lower and the Jark-Bear being more powerful at higher sample sizes, and both sort of leveling off right around a 92% power. So how you could use this graph would be to take your sample size and sort of draw up and figure out the first one test you want to use, all the way down to your bottom. Now there are tables that can help show these a little bit better because this graph is kind of messy, but this is a really great visual representation of how, as your sample size increases, in general, not always, with the KS, you're going to see that. So the KS actually does approach 100% in some distributions, and we'll see that in a second here, because underlying distributions have a very, very important impact. But how do we know the underlying distribution of our data? Isn't that what goodness of fit testing is for, such as normality testing? And that is absolutely the case. In real empirical data, there really isn't an underlying distribution, but we can use the visual shape of the distribution. We can use symmetry and tailoredness to sort of identify and distinguish between two different categories. So skewness and kurtosis are measurements of that shape, and they can actually help us to determine which test to use. So in most power studies, you'll see that they divide them into two different segments: the symmetric distributions and the asymmetric distributions. And you'll really see that most of these tests are less powerful when analyzing symmetrical data, which makes sense. I mean, the normal distribution is a symmetrical distribution. So a symmetric distribution is going to look a lot more like a normal distribution than will an asymmetric. And to me, these graphs just exemplify that so well. In here, the Kolmogorov-Smirnov is basically useless on symmetric distributions. On asymmetric distributions, it actually performs okay at about 25%, maxing around 30%. But on certain distributions, it will approach 100%. But when you have all these other tests, there's really no reason to consider the KS test, except maybe at very small sample sizes. But you can't really rely on your data with small sample sizes anyway. But if you look on the symmetric, almost everything approaches, the asymmetric, almost everything approaches 100% power very, very rapidly. Whereas with the symmetric, it takes quite a while. And the Anderson-Darling and the Jark-Bear actually never approach 100%. And that's really what was dragging them down on that previous one, which was averaged across the symmetric and asymmetric. So this to me is just an incredibly great, example of how the symmetry of your data can really have an impact on how reliable your normality testing is. So you could use like a skewness benchmark to determine maybe it's too symmetric to even rely on testing. Now that doesn't really help you, but it's something that's very good to know if you have very symmetric data. You just can't trust your tests nearly as much without larger sample sizes. But that doesn't mean that your data isn't normal, because for it to be normal, it has to be symmetric, which is exactly why it has much more trouble. These tests have more trouble with it. So, as I was mentioning, that the distribution has a huge impact, especially when it comes to the symmetry. But when we look at the t-distribution, which is a generalization of the standard normal distribution, we can see that the degrees of freedom actually have an impact. So just because we have a symmetric distribution doesn't mean that our tests are always going to accept. You'll see here that even though they're all t-distributions, different t-distributions have very different behaviors. I believe this top one here is the Shapiro-Wilk-Royston, or the Liliephores, and that purple is the other one. But just a fascinating group of graphs here, where we see as that degrees of freedom increases, which you'll see as it approaches infinity, that really does look like a normal distribution. Our tests almost always accept it, and that's probably because in the case of a distribution like that, again, just because it didn't come from a normal distribution doesn't mean the data is not normal enough. That's really what these tests are trying to tell us, is our data normal enough to have valid capability results?